In the previous lecture, we saw that at some point in the past, the universe was extremely dense and extremely hot. From this fireball, as space expanded and the matter cooled, it appears stars and galaxies condensed out and produced the universe that we see around us today. This basic picture of the universe as something that has a finite past and began in a hot, dense state is known as the Big Bang model of cosmology. And this week we're going to observe the three biggest pieces of observational evidence for the Big Bang. And next week we're going to get into a little more quantitative detail. So this lecture we're going to deal with the first piece of observational evidence that was found, the cosmic microwave background. So let us restate our hypothesis. Throughout the history of the universe, galaxies have been moving away from each other. Therefore, there was a time in the past when the universe was extremely dense and hot. The universe today evolved from this initial state, which we refer to as the Big Bang. The Big Bang does not occur in one place in the universe, it occurs everywhere. Every point in space was infinitely dense and infinitely hot. Space itself needn't have been small at the point of the Big Bang. In fact, space could have been infinite at the point of Big Bang. It's just that it was filled with an extremely dense hot plasma, and space expanded and the plasma cooled from there. So, prediction one. If we apply the laws of physics to the situation, we find out that until about 300,000 years after the Big Bang, the universe was hotter than the surface of the sun, about 5,800 degrees Kelvin. And we know by looking at the surface of the sun that if material is hotter than that, it is not transparent to light. In other words, photons will bounce around off of the ions that make up the material and will not be able to travel in straight lines for very far. But we also know from looking at the sun that once the material cools below 5,800 degrees Kelvin, photons are then able to move very large distances without colliding with other material. So they're able to stream freely, and most of them will not hit another atom or molecule ever. Now we know, again, from looking at the sun, that as you go from above to below 5,800 degrees Kelvin, the radiation that you release and that is free to stream out will be in the form of a black body. So therefore, as the universe cooled below this, as it aged beyond 300,000 years, it will release everywhere a bath of radiation that has a black body spectrum and has basically the same temperature. Now, as the universe ages and space expands, this radiation will have been redshifted. So it will not appear to be at 5,800 degrees Kelvin, which is in the visible part of our spectrum. It will have been redshifted, and if you do the calculations, the black body spectrum from the Big Bang should peak in the microwave. And in fact, calculations showed that it should correspond to a temperature of about 2.7 degrees Kelvin. Now, these calculations were done before any observations were made, before anyone found this radiation. So this is a direct prediction of the Big Bang. This isn't attempting to explain observations afterwards. So can we see this remnant of the Big Bang? Essentially, if we see it, we will be looking back in time onto the surface of the fireball that created the universe, kind of like looking out into space and onto the surface of the sun. Well, it was discovered in the 1960s by Penzias and Wilson, who were not looking for it. They were building a microwave telescope for other purposes, and they accidentally stumbled upon this microwave signal that came from every part of the sky. They won the 1978 Nobel Prize for this discovery, and this must rank as one of the most important scientific discoveries ever made, since it was direct confirmation of the prediction of a model for the beginning of our universe. In fact, if you still have an old analog TV with an aerial, some of the static you see when it's not tuned to any channel, about a couple of % of that static is the microwave background radiation. So you're seeing a little bit of the Big Bang every time you tune an old TV to static. Since the discovery, there have been 3 major satellite missions to measure the black body, the cosmic microwave background radiation. NASA's 1989 satellite, the Cosmic Background Explorer, was launched in 1989. WMAP, the Wilkinson Microwave Anisotropy Probe, was launched in 2001, and the Planck telescope was launched by the European Space Agency in 2009. So the three of them were able to get increasingly accurate measurements of the black body spectrum. And lo and behold, it is a black body spectrum. It is the most perfect black body spectrum we know in nature. It has a temperature of about 2.73 degrees Kelvin, and so almost perfectly confirms the prediction of the Big Bang model. Now, it turns out that, importantly, if you look at different parts of the sky, the temperature isn't precisely 2.725 degrees Kelvin everywhere. There are tiny, tiny fluctuations that COBE first measured and that WMAP and Planck have been able to measure with increasing resolution. And if you map the night sky out, these temperature anisotropies, as they are known, look like this. So in these maps, darker blue means slightly hotter than 2.725 degrees Kelvin, and the more red the color, the cooler the temperature below 2.73 degrees Kelvin. We are talking about fluctuations of no more than 1 part in 10 to the 4. So these are very small fluctuations. In a couple of lectures' time, we will explore the origins of these fluctuations.